welcome to Makers on Tap, the podcast where makerspace directors drink and talk about making stuff. Tonight, I'm your host, Joe, and we've got
Aaron
and Christian.
We're trying out this video thing for the first time, and it's a little different than we're used to, but you guys are going to see why. We've got a pretty special episode for you guys this time. But before we dive into that, Aaron, what are you drinking?
So we actually went to Indiana last weekend, and we stopped by and got some Three Floyds. So
I gumball head.
Got their gumball head.
I hate you.
It's super good.
Christian?
Personally, I am actually drinking a little bit of something called water for tonight.
Hey, me too.
A little late.
It's been a long weekend, and you know, the headache is already setting in. So
yeah, no, yeah.
And it's a special episode. The discussion's going to be short tonight because the episode this week is actually an interview from E3d's Sanjay Mortimer and me, and it ran a little long. The entire interview is slightly over an hour of some really great discussion between me and Sanjay about completely different stuff than you guys would normally get from an E3d interview. So we talk a little bit about E3d products, but we talk a whole bunch about 3D printing, some theory behind it, some fun techie stuff, and some future vision stuff that we would both like to see happen in the near and long term. It was a really, really fun episode for both of us to do. A little bit of background. Sanjay and I have known each other for a few years now, and we've had a lot of conversations like this where we just kind of like nerd out about what could be, and they always run down some rabbit holes, and I kind of let this interview do that because it was fun, and you know, I think it turned out pretty well. Do you guys have comments?
I think we want to get into it after we come back from the interview.
That's true.
But yeah, no, it definitely is a fun listen, and we hope that you guys definitely enjoy it.
Hello, welcome to Makers on Tap, the podcast where makerspace directors drink and talk about making stuff. Today, we've got a special episode for you guys. We've got E3d's Sanjay Mortimer, and this is a morning episode for me. So the drinks that we're having are a little less adult and more like water and apple juice. What do you drink?
Coke for me. Yeah,
nice.
I'm always on the Diet Coke addict.
Stuff's gonna kill you, man. Rots you from the inside out.
Yeah. My wife's a doctor, and she keeps telling me it's like a large cause of gastro cancer. Yeah, comforting.
Well, you want to introduce yourself, Sanjay?
Yeah, sorry, I did too much time on Coke. Yeah, my name's Sanjay Mortimer. I am one of the founders of E3d Online. We make hot ends, most famously the V6, but I suppose in general we're kind of like, we're an extrusion and R&D company in 3D printing. Whilst our like huge expertise is around pushing hot plastic out of tiny holes and doing so really well, we try and kind of look for hard problems in 3D printing and solve them, and then package them up and sell them to 3D printing companies or consumers. So, you know, the tool changer, for example, isn't an extrusion system, but it was a really cool, interesting, hard problem. That's kind of what we do.
Yeah. And we're going to talk about the tool changer some today. But, and, you know, to your intro, you don't always shove hot plastic out of tiny holes. You even have big holes that you shove hot plastic
through.
That's
true. We shove hot plastic out of a wide range of holes in various diameters, sometimes even shapes, various diameters and materials.
Sometimes shapes.
Yeah. Oh, yeah. But I suppose, you know, application has, the optimal like resolution. As you increase your diameter of your nozzle, your maximum flow rate increases, but your resolution goes down. Converse, if you go to smaller nozzles, more resolution, less time. When you get to very large nozzles and very large sections, and if you want to lay down in certain ways, it can sometimes be advantageous to what you're trying to do when you're forming a bead of plastic on your print is you're not actually trying to end up with a cylinder of material that's laid down. You're actually trying to end up with a shape that's called a stadia, which is a rectangle capped with two semicircles.
Okay.
Right, so it's a round-ended rectangle. It's the shape of a stadia, right? Look at Olympic stadium. Yeah.
And every time we talk, I learn something.
Yeah, that's the name of the shape. So, like, because you've got the nozzle at the top and you've got the print or the bed underneath, and so you've got these two planes, and then you're injecting the fluid into the middle, and the fluid wants to do its standard fluid thing,
Right.
where it comes out and forms a meniscus at either side. What you actually end up with is a stadia. And at the tiny scales that we deal with on our like day-to-day basis, squishing the material into the stadia shape is very low effort and unproblematic.
Yeah.
But when you get to some very large scales, you kind of and very high flow rates, the actual like the splurging it out into that stadia shape and that aspect ratio. But I suppose particularly it's less about absolute size, but more about the aspect ratio. So if you want a very wide, thin layer that you want to put down. So let's say you want to put down I don't know, call it a 1 millimeter, just for the sake of numbers, call it a 1 millimeter layer, but that layer has to be 10, 15 millimeters wide.
Right.
Then you're kind of squeezing plastic out of a hole in the middle that then the nozzle has to squeegee down. There's a lot of pressure involved, and also the nozzle has to stay in place quite rigidly. So in that case, maybe you can consider like trying to extrude a ribbon, and then you have less work to do in terms of deformation of the fluid after like post facto exit of nozzle.
Yeah. Well, even when you're looking into things like paste extrusion, when you're trying to do big fat layers, also wide, I know some of the research in things like concrete 3D printing, they've actually looked at square nozzles and hexagon nozzles because
and
of
rollers
all this
as well.
Yeah.
Which is kind of a neat thing, and people have done that in plastic as well. So you like have a roller that follows the head on a slewing ring. So a thing that attaches the nozzle and rotates such that the roller is always following the path just behind. And so the material comes out and drops down as a cylinder, and then the roller squeegees it into place.
Yes. Yeah, and then they have side dressing that comes back on the sides too. That like it looks like a scoop like this, and the material's flowing. This way, and they just kind of like to dress the walls as the it's flowing.
Oh, I see. Yeah. I mean,
super cool things. Have nothing to do with
there's so much prior art in this, right? So the thing that like everyone must remember is that everyone's like, "Oh, isn't that fancy and isn't that complex?" Right? But like, I don't know, you got a window behind you. Is that a PVC window by any chance? You don't have those in America. You don't really use double glazing. You just burn.
Yeah, that's PVC.
Yeah. And so that PVC extruded section is like absurdly complex if you look at it.
It is.
And so they extrude those out of nozzles, obviously that have roughly that shape, accounting for some like die swell and deformation. But then to hold everything square and central, they have like vacuum plates that stuck onto the thing, and they use like a surface effect. So there's I forget what it's called, but where you have like the Bernoulli effect, where you have the high speed air, and when you blow on a piece of paper and it sucks up. They do that. They do that to stop the extrusion like collapsing and shrinking in. They blow air like this, and it like holds the extrusion in place in a non-contact fashion. And then Like, and people are
Oh,
always like, oh, I mean, it's so hard making filament exactly round. It's like we can do better. So extrusion is something that humans have become quite good at. And frankly, in the 3D printing industry, we're kind of rank amateurs when it comes to complexity.
yes.
Um, in terms of miniaturization and precision and things like that, um, we've got a lot more control because most extruders just run open loop steady state for the most part.
Yeah.
But like in terms of as it's being output, we just squish it out of a circular drilled hole, right?
Yeah.
But there's a lot of prior art in that field, and there's a lot that could potentially be done, I suppose.
Well, that took a rabbit hole. Segues are hard,
Mhm.
but also very
Oh,
fun.
yeah. Yeah. Do we
No,
do we have a structure? What are we supposed to be talking about, Joe? This will
I,
last all.
I, you know, our episodes have a rough structure, but so far the interviews have been very freeform, and like I have these scribbled notes, that are terrible, but the other two guys on the podcast cautioned me this morning. They're like, "Don't let this get too technical," and I was like, "Nah, it's gonna be technical because that's what's fun." Um,
Yeah.
to give you guys some background, Sanjay and I met at Midwest Rip Rat Fest a few years ago, and we've been talking on and off on the internet for these random concepts for the last few years, and our conversations are always very entertaining and take these wild turns like they just did. So that probably won't be the last one. But I'm gonna try to keep to my script here. So to start, how are you guys? How's E3D? How's Sanjay? Like,
E3d is crazy. How's Sanjay? I just got married. Uh, 3D
yeah,
printed ring.
nice.
Yeah. Yeah, it's hardcore.
I machined
She was like,
mine, but
you're not allowed anything 3D printed at the wedding. No talking about 3D printers. You've got too many of your colleagues. And yeah, snuck in the rings.
nice. That's
Um,
awesome.
yeah, but yeah, E3D in general is big and growing. It kind of blows my mind. You know, I keep thinking that like surely everyone who wants a hot end must have one by now, but that never seems to turn out correct. Um, where how have things changed? We moved into a big new building. We grew quite quickly, and we ended up spread across kind of 5 units in this business park that we're on just
Oh
outside of
wow.
Oxford. Yeah, and it was kind of this higgledy-piggledy, like we had one unit and then we managed to get the one next to it, and then we needed more space, so we got a shipping container, and then R&D was too noisy, so we were like, well, we'll move that to another building, and then manufacturing outgrew, and so it goes, and all of this occurred in the space of 18 months, so there's like not enough time to get the correct type of building that you want,
Yes.
or to it would be completely absurd to have moved 5 times in those 18 months,
Yep.
right? And also the buildings weren't available. And so we're just sitting there. And then this place came up. And so it's basically like 3 large warehouses, like warehouse rooms.
Okay.
Um, like, I don't know what you call them, but like the big shed shaped things,
Yeah,
like
yeah.
warehouses, like 3 of those next to each other, joined together. Um, and that's how we got it as an empty shell. And we've done the kind of Elon Musk epoxy floor thing, and we've installed offices in the upper level. So we put in a floor, if you like.
Okay.
Um, and so that was a big ordeal, and we just moved in here in January, um, thinking, this will last us forever, but it's full now.
Yep.
Um,
That's how it goes, man. That's exactly
yeah,
how the startup I work for is going. We just moved and we're already trying to buy the rest of the building and debating on building a building in the field next to us. It's crazy.
yeah, we're gonna have to build another floor, but yeah, overall, it's go- uh, you're gonna have to. Sorry, people are. Sorry, we've got tannoy systems, and
Ah,
then
yeah, yeah.
I'll explain in a second. Hang
That's why we don't record live.
on. So Yeah, we've got IP phones throughout the building, and all of them have a speaker on them. And then, if you know the secret code, you can press in and make all the speakers in the whole building like on your hot mic. It's cool. Anyway, but yeah, so we've grown rapidly. We're up to like 40 people now, which is pretty insane. Um,
That's
we're
awesome.
we're we're making a lot in house. We do like loads of hot end assembly, like all the ALF objects, lolsbot hot ends. We're building tons and tons of those. And for other companies like BCN 3D and many others. So there's a lot of like building actually of hot ends and extrusion systems happening like literally below my feet right now, which is kind of neat.
That's so exciting.
And we're kind of bringing in-house more and more.
That's crazy. So
Yeah.
with all that going on, what do you do outside of work for fun? Like what's Sanjay after 5 or 6 or whatever you guys work over there till? You just hang out?
Go home and sleep. No, I know it sounds like a corny answer, but like I
No.
know 3D printing is my life, you know.
Yeah.
And when I can at the weekends, I come in and I kind of, because I don't get as much time to do R&D while I'm at work. I kind of always have a queue of people that want something or some meeting. So I try and come in early or late or at weekends and kind of just, or bank holidays, and just like fiddle with my own like little concepts and ideas and get some time in the workshop. That's a big one.
So you're my
But
favorite kind of engineer. You're the
what's that?
You're the engineer that's like the 9 to 5 engineer, but then when you go home or when you're off work, you're like, I could be working on this. This project's been eating at me. I need to do this.
Oh man, like you have no idea. I think that my problem is that when I have like a problem or a project, it just becomes like all consuming. Like wake up at 6:30 a.m. and yeah, we'll talk about the one that I'm on at the moment. Yeah, which is like how do we build the kind of, so V6 was designed and built for having contract manufactured machine parts come in and then having the user assemble them and having an experienced user and so on and so forth.
Right.
So you have this like heater block and a heater cartridge and a sensor, and they're all separate kind of modular elements in and of themselves, which they're each, a sub-assembly. A heater cartridge in itself is a non-trivial piece of engineering, and so is the sensor cartridge.
Right.
And all of those go into the block, and the block is like an all sides machined milled part, and then and so it goes. So there's quite a lot of, in terms of like broader market trends, the reality is that what we need to do to adapt and stay current is to reduce costs and improve usability.
Mm-hmm.
And that's an interesting problem. Yeah, I'm a big, obviously, like printing performance nerd, and so we're seeking to make improvements in performance as we go, but never at the expense of usability,
right,
and cost effectiveness. Next generation hot end. So what we want to do is be able to provide something that serves the function of the nozzle, heat break, heater block, heater cartridge, sensor, fixing, all of that in like a single, self-contained, easily swappable unit that is extremely cost effective.
Mm-hmm.
Because at the moment, the reason why a lot of users don't change out their nozzles for whatever reason, even though they'd have great benefits from doing so, is because it sucks. Like, it's a sucky process.
Yeah.
And also, when people experience problems, troubleshooting then sucks as well, because you've got a nozzle clog. Well, you can buy this little £5 part, but then you have to do this process. And a lot of times people are like, well, I'd rather just pay the 50 and exchange the whole hot end and not have to deal with that. And that's kind of a crummy situation for the user, because they're throwing out loads of good stuff just because of one small. And so I think if we can make these little parts that are cost effective enough, but really easy to use, exchangeable parts that you can buy exactly the one that fits your needs, and also swap it out as you need, kind of more regularly. Like, again, the biggest impediment to people swapping out nozzles for the reason why you don't swap out your nozzle for every print to the correct one is because it sucks.
Yeah.
Like, it takes it'll take you 15 minutes by the time you've found your spanner and heated everything up, and like instead we want to like undo one like latch,
Yep.
clunk, undo a connector, slide it out, slide the new one in, clunk the latch down, plug the new one in, printer's good.
We spent a bunch of time talking about this when I worked at Lulspot, when we were working together. So this isn't a new problem. This is a hard problem.
Correct, yeah, and it's the kind of problem we like.
Yes.
Because you solve the hard problems, then you're adding value.
Yes.
Yeah.
Yeah. So you guys just dropped a whole bunch of crazy high temp stuff. Like the high temp heater cartridges that get the temperature of the sun, and the heater beds that you could cook pancakes on. Like,
easily.
So what's going on with all that? What's the intent? Because
backstory.
Yeah.
We were approached by Airbus, the University of Exeter, and a company called Victrex. Victrex are the largest manufacturer of PEEK polymers in the world, and they were like, together we should be able to develop a formulation of PEEK that can be printed really easily. For certain values of easily, right? But nonetheless.
Can be printed.
Can be printed, yes. It is not totally impossible to print usable objects. And so we've been at that for like 2.5, 3 years. Material development, especially when it comes to polymers, is fundamentally slow because you have these like reactors that yield 1 ton of material, and you have to like these whole synthesis cycles, and we're talking about like $100 million worth of equipment. And it's not like they get much time to like bring it down to do prototyping, because it has to, the ROI on these things are 10 years or something. So they have to make the machine do the work. Otherwise they're losing revenue every day. But they found a really cool way to prototype. They actually built an entire mini reactor, like a miniature. Yeah, anyway, it's cool. But what it meant is that we could take PEEK and we could tweak it at the molecular level. This isn't what everyone else is doing with polymers, where they like take some resins and mix them together and add additives, where you then end up with this kind of polymer soup of maybe like some different kinds of chains with some additives inside. We're talking about actually fundamentally changing the way the chains are assembled in the reactor, which is very powerful, and you can do a great deal more. And I expect to see a lot more of this happening in the rest of the polymer world outside of PEEKs. I think that's very exciting. So we worked with them to develop this material, and that's been really successful. We're bringing this PEEK to market. Again, it's fundamentally slow to like make enough of this stuff, but it's on the way. It's happening. So watch this space. But what we ended up with is a PEEK material that you can print without a heated chamber, has higher Z direction strength than Ultim printed on a Stratasys Fortis 900 MC.
All right.
It even outperforms their new PKK Antero 880 material. And we're printing it in an open chamber, right?
On E3d hardware that like normal people can afford.
Yeah. So you can take like any consumer. So the idea is that you should be able to take any kind of decent middle of the range 3D printer, or certainly if you are a printer manufacturer and you already have a printer and you want to uprate it, all you should really need to do is change out the heated bed to something that's quite a bit more powerful and upgrade the hot end to something that's also quite a bit more powerful and slightly specialized. And so what we need to do is be able to achieve heated bed temperatures in the region of 150 to 200 and hot end temperatures of 400 plus, and exclude drafts. So you don't need an enclosure, but you just need to stop, like, the air conditioner blowing on the machine.
Right.
There are a bunch of performance enhancements and gains that you can get by doing more complex stuff, but let's not go into that because all our benchmarks are on actually a converted big box machine that just has a piece of acrylic slapped over the front and an open top. We changed out the heated bed to one of these Mordor beds that we're now selling, and changed out the hot end. The Mordor bed, I think they were codenamed Mordor internally, I think, on the website.
I like the name.
Something more professional, like high temperature heated beds. But they're a sheet of aluminium tooling plate that we start the anodization process. And in anodization, you open up the pores on the oxide of the aluminium, and then you impregnate it with dye, and then you seal it. So we start the anodization process where we open up the pores, but then we don't dye and seal it. We take a semi-cured silicon heater mat, and we use heat and pressure to squish it into the pores of the surface of the bed, and then we vulcanize it in situ. So this is really, really different. Something really important to get across. This is very different to other silicon heated beds, because other silicon heated beds, they have an adhesive interface layer.
Yes.
And that adhesive interface layer is usually 3M467MP, which is that classic self-adhesive that kind of smells like it's got like that fruity bubblegummy flavor. That smell to it. The stuff like the same stuff as on blue tape, right?
Yeah.
But all that stuff all goes to hell above about 100. It kind of turns into chewing gum, and the heater falls away. Whereas we're vulcanizing high temperature silicone rubber into the pores of the aluminium. And so that means that instead of being limited to 100, 120, we can go to 200 to 250.
That's
without any drama.
That's very exciting.
And it's got a thermistor built in, and it's got the mounting points have slots so that the standoffs that you put it in, they have slots that deals with the thermal expansion of the aluminium, and then we're including very high temperature insulating standoffs, so you can basically bolt it directly to something below even a printed part without melting that printed part.
Very cool.
If you use a brass standoff and you bolt it onto a printed part, then the things will not go well for you.
No.
But with these standoffs, they're polyphenol sulfone, PPSU.
Okay.
These standoffs, so as long as you put some insulation underneath to stop the radiated heat, then you could, I suppose, just bolt it directly onto printed parts. So that's the heated bed. They run off mains because they need like mad watts.
Yeah.
So there's appropriate cautions to be taken there, and solid state relays to deal with. But these are high end parts for like kind of quite industrial applications, and if you don't know what you're doing, then really you don't need to.
Yeah.
Like it's for that crowd.
Yep.
It's like the hyper enthusiastic maker that really knows what he's doing and wants to take on a big job and those safety implications, or it's for industrial manufacturers of 3D printers. People that can look after themselves when it comes to mains, right? So there's those, and then we've got the heater cartridges are kind of neat. They use totally different wire on the inside that's not nichrome. It's got like high melting temperature, lower oxidation. Then they pack it in. So, do you know how heater cartridges are made?
Yeah.
It's really crazy. And yeah. And so the packing ceramic is it's not magnesium oxide, I believe it. think it's an alumina, higher conductivity alumina. The whole object, the reason why heater cartridges fail is because of like hot spotting and expansion and burnout. And so in order to improve their life at temperature, which is the problem we're trying to solve here, is that normal heater cartridges, they don't have a very good life at 400 plus.
Right.
In fact, sometimes it can be tens of hours. So it's kind of useless. So we build the heater cartridge such that it evenly distributes heat. There's less hot spotting and buildup, and it's better at transporting heat away from the coil that's inside into the hot end.
Okay.
And so the insulation is a higher conductivity insulation that's packed to a higher packing ratio. And then the casement itself is coated in, I don't know what it is. The manufacturer is being very stum on quite a lot of things about these heater cartridges. We kind of developed them in hand, but yeah, they've changed basically everything. But they've got this coating on them that's kind of like it feels kind of soft to the touch, almost like, there's like soft touch polymers you get. It feels kind of like that, but it's obviously not. It's like some carbon, it's black. It's like some kind of conformal carbon coating, and it deforms when you clamp the heater block around it.
Okay.
It's like thermal paste, right? It does the same job as thermal paste.
Yeah.
So it's like a conformal coating that aids heat transfer from the case of the heater into the thing that you're trying to heat, in this case, a hot end. And by doing so, by increasing that thermal transport and the evenness of the thermal transport, you end up with less hot spotting inside the heater, and therefore longer service life.
Awesome. And excellent. So I'm just kind of going through my list. I'm bad at lists. But like, that was a really good explanation of why you guys have dove into the high temp stuff. Because I think when it first came out, a lot of people were like, well, why? And we've already got heat hotbeds that can make 120, and whoever needs to go higher than 120. And it's people. People need to go higher than 120 occasionally to do crazy, crazy things.
It's not for everyone. It's for, if you need it, you already know about it.
Right.
To be clear, like if you have to be asking these questions, you probably don't need what we're selling.
Yeah.
If you're wondering, is this for me? Do I need it? The answer is probably no.
Yeah.
I probably shouldn't say that as, the person standing to profit from you buying it, but that's the reality of the situation.
Well, a lot of what you guys are diving into, it kind of falls into that. And one of those projects I'm sitting here fiddling with is Super Volcano. Volcano is so cool. It's what I've been dying for years with my crazy tall 8-foot tall printer and some of the other weird projects I've built, but it's not an easy thing to use.
No, you've got one that you're printing with it, right?
Yeah,
sweet.
And it's really fun. The other night I was printing 0.6 millimeter layers at 150 millimeters per second with PLA at 190C. So
sick.
But
that's cray.
It was really, really fun to print. But when you are printing with melt zones that are, here's a nozzle from the Super Volcano. So your melt zones are like 2 inches almost. You really start, and you're printing these big, huge, fat layers. You really start fighting polymer issues like heat latency. And it becomes far more about how fast can I. It diverges far more from how fast can I melt this material to how fast can I cool this material.
Absolutely, yeah. Because the surface, the volume goes up.
Yes.
As a square factor, but the surface area goes up as a linear factor, he says. The cross section is squared,
right,
and the circumference, as a circle increases in size, the area goes up as a square factor of the radius. but the circumference only increases as pi radius, right? So as you go up, the amount of heat in terms of the number of joules of energy that is inside of there goes up, but your wattage dissipation does not go up at the same rate. And so that means that the plastic stays hotter for longer.
Yes.
And this is a fundamental, you can't really get past this. This is geometry and physics.
Yep.
Like it's nearly a mathematical truth.
Yeah. The way to get past it is more air displacement around the part, just pumping constantly to cool that surface off. And that's what I've been fighting, is trying to get enough air to it. So right now, my solution is 2 50 millimeter blower fans that are 12 volts running at 24 volts at full blast. So
you think you're cool, bro? You think you're cool? I'll take a picture of our setup downstairs, and you'll be so jealous. So we've got the shop air compressor hooked up to solenoid flow control valves.
Yes.
And we've got like 2 pipes like coming in, and you can dump like 3. I think it's like 5 bar goes in there, and lots of air comes out.
Yeah.
Lots of air.
The only reason I'm not doing that is my air compressor currently, it blows a lot of water when I let it freely flow like that. So
yeah, we put filters on ours and everything to stop that, because it would kill the layer adhesion, right?
Yeah. So I'm gonna get a desiccant dryer put in line and then start doing that. It's gonna be real fun. I'm so excited for Murph this year for all of the hilarious things. But one of the things I'm really excited for, we talked about this a little bit ahead of time, is at ERF, I kind of fell in love with the belt printers. I spent a bunch of time talking to Brooke about his printer belt and talking to Bill Steele about his. And I have yet to build one, but one of my super volcanoes is going to go on a large format belt. And the Massive V2 is my plan. My Massive V2 will be a belt printer, and hopefully by the end of Murph, I'll just have a whole table taken up with a rocket or something being printed sideways instead of super tall like last year.
Yeah. I don't know if we can talk about everything, and I've got to watch my words here. But Brooke proposed as well. Tool changing belt printer.
Yeah.
So that would be super cool, right?
It would. Maybe we should talk about that offline.
Yeah.
Carrying on.
But yeah, I think belt printers are very cool. I mean, they're obscenely cool.
Well, the thing that makes me excited about them is, like, you've got this conveyor that I could be constantly cooling with the conveyor. Like, I just have stationary nozzles around the print. And
oh, okay. Yeah. So I have like a laminar flow.
Yeah.
Like, have you seen on the Stratasys machines where they have the big, like, it's like a snail blower, but stretched prismatically.
Is that
and they produce
on their like infinite build area machine where they're building sideways?
No, this is they have these. You can't really see them, but they're on all the dimensions of vortices. But it's it's an air blower. So it's like a blower fan, but a blower fan is thin. They're only like 20 mil thick, right? You get a 50 mil blower, it's 20 mil thick. Imagine that, but 1 meter long.
Oh.
Yeah. So you have this big stretched impeller, kind of like what's inside of an air conditioner, right?
Okay.
You have the big long bar. So you can buy those that are like one print area long, like 300, 200 millimeters. And then you can produce a laminar sheet of like moving air that is like a cross flow over the bed. Some Ultimaker printer people do this because they have that motion system has a consistent plane of where the action is happening.
Right.
And you can jet air right across.
Interesting. I'm going to have to look into this. Thank you.
Yeah. And what's neat is they have them in ovens as well, right? So you can, and hot air heaters.
Mm-hmm.
And so they make hot air heaters that are also these. So you can like do a heated chamber and all in one. Yeah. It's
Yeah.
good fun.
Very cool. All right, so you brought up Tool Changer, so I'm gonna bug you about it. Everyone bugs you guys about Tool Changer, so I was gonna try to leave it out as much as I could. But where's it at? What are you excited for? I'm super excited because I'm in beta 30. So,
Ooh, look at me. I'm a fan. I'm saying his favorite.
hey, yeah, that's exactly how I feel.
It's true. Yeah, no, you are.
So yeah, where are you guys at, and what is Sanjay the most excited for with Tool Changer?
So, Tool Change is going well. I'd say that it's like bang on schedule thus far, which is really cool. If not, so some of the bits are ahead, and the things that were concerning me, like the little risk parts that were being tricksy, they're all resolved now. So, and all, yeah, everything's so all of the, yeah, okay. So back up. The tool changer is going to be sold as there's a motion system. Then you can buy the tool changer parts and you can bolt the tool changer, i.e. the thing that picks up the heads. You can bolt that tool up picking head, which is a separate product,
Right.
onto the motion system. And then you can buy your tools as you see fit and clip those onto the motion system as well.
Right.
Add electronics, and you have a fully functioning printer that has a range of tools on it. So,
But what I
first
heard you
product,
say is this is
yeah.
not out of the box a fully functional printer.
Oh, you shut up.
No, even
Yeah.
even the people that I think get this don't get this. So we'll beat on it for a second. It's not out of the
Yes.
box a fully functional printer. It is a motion platform.
Yeah, well, maybe we should back up to our objectives here.
Okay.
And then people will understand why and how this is going down. Our objective is to proliferate the concept of tool changing throughout the 3D printing community, both commercial and hobbyist. In order to do that, we are providing a reference platform in terms of both a motion system that can carry it, a reference implementation of the tool changer, and tool reference implementations. You can buy any part of that system individually and use it to build your own ideas. Your idea may be, I want a tool changing 3D printer and I want the lowest effort route possible to that. So you buy the motion platform, you put the compatible tool grabber onto it, and then you load it up with tools from E3d that are ready to rock. Alternatively, you may be a company that already makes 3D printers, and you're like, well, damn, we could do with tool changing. What I'm going to do is buy the tool changing grabber, find a way to integrate it into my printer, and then buy the tools and find a way to integrate that. And maybe it doesn't quite fit. We'll chat to E3d, figure out a solution, and go from there. And then as a hobbyist, you can do much the same. So again, our objective is to proliferate tool changing among the whole 3D printing community. So backing up, we have the motion system, which is the first puzzle piece, if you like.
Right.
It's the most expensive, longest lead time part of the system. It's not super complex because it's well designed as a simple system, but it's got some of the most expensive long lead time parts on it, like linear rails and stuff. So that is all in-house. Literally everything to build the motion systems is here. They are putting together reference, well, not reference implementations, but they are taking the manufactured parts and they're putting them together and testing them as we speak. So Greg is on that with Dylan right now. All the tool changer parts are on the way and on order. So this is for, when I say the tool changer, what I'm talking about is the head that can pick up tools.
Right.
So the head that can pick up tools, aka the tool changer, is fully designed, tested, and on the way. There are a couple of parts that cause delays on that. One of them was the little gear that goes on the servo. It's really annoying because servo manufacturers, they don't reveal the geometries of the splines on Yeah, it's really annoying. Anyway, we've figured out a way to get a good mod 0.5 proper metric non-proprietary gear onto this proprietary mess of a spline on the servo, and so that's all fine and dandy. And what was the other little thing that was causing issues? Oh yeah, Highwind being a pain with the rails. They wanted like 6 months, 6 to 8 months to produce the rails, which is just anyway. After some gunboat diplomacy in that like we will buy them from somewhere else. The lead time has now dropped to 3 months. So. But those they've been ordered some time ago. Anyway, they're on the way. They had enough stock to cover beta 30, so the first 30 machines, but obviously we have to produce several hundred of these things ongoing.
Right.
So the motion system's in-house, being built, very high confidence. It's already working. I've seen it downstairs. It's going to be great. It's such a simple system from a engineering geometric complexity standpoint. It's fine. The tool changer is going to come in. That will need some serious testing because I don't have to worry about high wind rails lasting, 1,000 cycles, but I do have to worry about the tool changer lasting 10,000 cycles because we built it, and the wear surfaces and things like that. So we've observed wear on the early brass prototypes. So we're moving to higher wear materials like silicon bronzes and hardened steels for those wear contact points. So that's going to require a bit of testing, but we're very confident that it's going to work. And the high-risk items, i.e. the wear contact points, which is the ramp ring where the pin goes in and locks, that's a separate removable part.
Yeah.
So if we need to change the design of that, we just have to design this little, a new little ring that maybe changes the angles or increases the hardness or whatever. So it's a very low-risk way of building it. And we've had this design of tool changer functioning for a very long time. It works very, very smoothly.
Awesome.
So that's on the way. Tools are, V6 tool is super simple, designed, built, tested. It's the kinematic coupling balls, machined aluminium plate with a, L like standoff block, and we use the threaded heatsink instead of the groove mount. And so that makes things super simple. So that's all good. That's kind of your sit rep on the motion system tool changer affair. So all going well, risks ironed out, a little bit of testing to do on the tool changer for kind of longevity, but very confident about the functionality. And we're kind of off. So what we have now is a logistical problem, not an engineering problem for the most part. So it's kind of out of my hands in many ways, which is nice.
Well, logistics can be sorted out. That's easy. Now that we know it's possible, logistics are fine. Very cool, very exciting. So, what are you excited for with the platform? Like, what's tickling your Sanjay with it?
The push towards release has hampered our ability to build tools because I've basically dictated to the team that we're not working on any tools until we have a system out in the wild that people can purchase.
Right.
To prevent distractions. We have to race towards product. But the array of tools that we want to produce is going to be super cool. We had an intern summer intern who, incredible guy, super smart. He's gone back to uni to finish up his degree, but part of his project will be a pick and place tool. So he's taking on what will be quite a complex tool in the system. And it's a really exciting pick and place tool. I won't go into all of the details because it's his academic project.
Okay.
But it's, as I've discussed in talks before, it's not pick and place for SMT chips and stuff. Right. We want to place useful mechanical objects into parts and be able to pick up a wide array of very oddly shaped parts. And the design, it's like a tool changer in a tool changer.
Okay.
Yeah, it's like tool changeception. But I'll leave it at that.
Okay.
So it's going to be super neat. Cameras with collimating lenses. So you can do metrology. That one's mainly a software problem.
Yeah.
The
That's going to be
camera's been designed for a
an
while.
interesting problem to solve software-wise.
Yeah, yeah, absolutely. But we've been doing a bit of machine vision here now for QC actually, checking concentricity of PTFE tubes with. It's really freaking neat. Minor sidetrack, we have a machine that quality controls the PTFE tube by shining infrared light down the tube, which conducts like a fiber optic.
Okay.
And then that gets pressed up by the machine against a microscope slide that uses an IR camera. This is all happening in a dark box through a collimating lens, and it measures and that gets the concentricity and then automatically cuts the tube to length and then pushes that up. Yeah, it's freaking baller. It's like this little machine. It cuts the little lengths of PTFE that you get with your hot air. Yeah, it's freaking sick.
That is far more scientific than my method of like stretching the PTFE out on the steel scale and then going, looks right, and with a single edge razor blade. Far more scientific.
Yeah,
love it.
But the thing that we're checking for is the concentricity of the hole, because the process by which PTFE is made, PTFE tube is made, is not like normal thermoplastic extrusion.
Right.
Anyway,
it's like a sintering process, isn't it?
Yeah. It's kind of like they extrude it and then they sinter it, and there's a lot of opportunities for the tube to deform throughout the process.
Right.
Anywho, computer vision. We have some confidence that we'll be able to at least get that started into a usable open source project, and then people who are more competent at software than us can come along and integrate it and make an Octoprint plugin and so on and so forth.
Right.
But effectively, what we intend to do is basically compare the G code against the image that we get back.
Okay. Yeah.
And then display you a diff. So hopefully, like, everything's green, but when there's like material where it should be, where there's material where it should be, it'll be green, and where it shouldn't be, it'll be red, and when there's material missing, it'll be black, something like that. You get what I mean?
Yeah.
So that will be really fun, but that's a big software project, easy hardware project. Then it gets into the weird stuff, and this is what I like really want to get into. I'm really raring to get into, but I'm kind of held back because we have to deliver to the customers that we've promised and taken money off of. But once we've fulfilled our obligations and got product to market and have product in people's hands, then it's onto the weird tools. So weird tools are like physical metrology and hybrid stuff in all of the ways. So one of the guys hacked together really recently that we didn't have much confidence that it would work, but it was worth a go, was actually using have you seen drag knives?
Mm-hmm.
So they're like absurdly sharp little razor blades that are designed for trimming like, these 100 micron sheets of material very precisely. And so we wanted to see if we could like print a 100 micron layer and then trim it back to precisely so, and then rinse and repeat.
Yeah.
Because if you can do that, you get rid of all this like motor spindle on the tool head, chatter, cutting, heating, horror show, and you get these like perfect razor cut, sheared edges with the nice surface finish. More experimentation required.
Yeah, it seems like would be a difficult because like drag knives live off of down pressure. That's how they like circumvent corners and everything.
And so like if you have like you would need a great deal of support material where you wouldn't normally have it, for example. And there's a whole bunch of issues there and obvious geometric limitations with regards to overhangs and things. But if you have a tool changer, then you can pick the tool for the job, right? That's super. The drag knife is kind of just. It was easy, right? Because we bought a drag knife off Amazon and put it in the V6 holder and just kind of bolted it in there with a printed part, and we're like, okay, let's like whiz this around a print, see what we can do.
Yeah.
So that's kind of neat. the obvious one is the mill, which is, obviously, as people keep telling me on the internet, that's never going to work as a milling machine. It's not a milling machine. It's a 3D printer that trims parts, right?
Yes.
So yeah, the design of the spindle and everything for that, like a very small BLDC spindle, and or in a lot of machining centers where you have like live tooling and tool post holders, especially ones with high pressure through coolant ability, you have these cutters that have a turbine inside. So it's a spindle that doesn't have a motor, but you hook it up to the through coolant.
Yeah.
And so in this case, you hook it up to the air behind, and it's like a spindle, but it's super small, very powerful, and absurdly high RPMs.
Yeah.
So it's like dental drill grade RPMs.
RPMs. That's wonderful.
RPM. Yeah. In the itty bitty package that's effectively, Bowden powered, because the physical power source, the prime mover is off carriage. So that's pretty neat.
And those are fairly low air usage, so you don't need super high CFMs. You could run those off of a small compressor. No, small.
Yeah, I don't know what the consumption's like. I will take your word on that. I'm not an expert on those systems, but I suppose the thing that concerns, or the interesting part of that, is that suddenly you're introducing a lot of air into your system, and I think this is going to be one of the fundamental issues that we're going to have to overcome with hybrid, is that printing and cutting have some different physical requirements.
Right.
And so in cutting, you want to like flood cool everything and chip evac everything. Like if you could, you'd flood it with some plastic appropriate coolant, be that air or mist or what have you. However, if you use a fluid that is not air, then that's just not going to fly, because you're going to leave residues on your layer interfaces, and your part's going to lose all interlayer adhesion. And even if we're just using air to cool the part, let's imagine that we're printing a useful engineering plastic, so PC, for example. We want the PC to stay very hot so it doesn't warp while we're printing it, but then we want to drastically and rapidly cool it while we're cutting it so it doesn't gum up on the cutter.
Well, I think if we're just cleaning up layers, you're just cleaning up the little layer issues, you probably won't have to mess with coolant much, or even air. Because it's such a low cutter engagement. You keep your RPMs in the right range, I think you'll be fine. Because most of the plastics that we're printing cut really well. I've machined a lot of printed parts.
Yeah, no doubt.
So,
I'm interested in your experiences there. I mean, we're going to be making like tiny powdery chips.
That's my main concern, is just cleaning off the layer interfaces, and maybe that's just like a quick air blow. From like,
so I'm kind of thinking that
cooling fan or something.
I'm kind of thinking that we have like air jets of controlled temperature, so we can apply force without. So we can decouple cooling and chip evac.
Like, have you seen the hybrid DLSM or DMLS machines that companies like Sodic are making, where it's...
So do you mean so there's one by the Japanese company that's actually like powder bed DMLS?
Yes.
Or do you mean the big like laser blast the powder into the laser beam on the machining center?
I'm talking about powder bed, so not lens like Akuma's doing, but actually the powder bed. So they cut, they do like 2 layers, and then they go back and then they machine them, and it's all done.
It looks badass.
It works surprisingly well. I spent a lot of time talking to one of the technical guys at IMTS this year.
Oh, interesting.
So we can dive into
because the mold guys are like, The mold guys are super into that stuff.
Yeah.
Like the mold people are going crazy because you put the cooling channels and that. Yeah.
Oh yeah.
Like, absurdly high productivity molds. It's cool.
And they're getting crazy tool life out of 1mm end mills because they're taking such a little axial depth of cut.
Yeah.
And
And the wear is like it's like some cubic factor of your engagement and pressure, as I understand it.
So we're like running longer than any podcast I've ever recorded. This is great.
No, we're only halfway through, dude. Hell, you can cut it down. You can always make it shorter.
So what's next? Like, we build the tool changer. The tool changer works. The tool carriage thing that you've talked about in past videos, that thing works. So we could get like a 20 tool head tool changer 3D printer. That works. What's after that? What's E3D in 5 years? What's the dream?
Yeah. So in terms of major projects, we got to finish up the tool changer. There is Titan V2, which is going to be like from a commercial standpoint, it's going to be really, really nice. It's going to be an extremely high performance hot end extruder combination at a very competitive price point. That's all I'll say for now.
Excellent.
Because it's a very commercially driven project and it's quite somewhat commercially sensitive. It's actually not hugely, like massively technically interesting.
Okay.
It's just a well executed, tight design of known principles that we already have out there among the 3D printing world, combined into one, done in a really tight package that's very, very highly optimized for design for manufacture, in essence. So we can crank out a very high-end extruder at a very low cost.
Okay. So you guys, as we've talked throughout this whole interview, you've mentioned commercial quite a bit. Is E3D changing its focus from the maker community to commercial community, or is the support for the makers still there?
So I think that what E3D does quite well is like catering to the whole spectrum, including like very weird applications. So our intent is never to serve like this particular sector very well. We seek to serve particular customers very well by like creating custom solutions. But I think that E3D's like fundamental market advantage is that we understand the underlying science of extrusion and how to design extrusion systems that work in a wide variety of circumstances for a wide variety of specifications. I mean, we basically have a bunch of Excel spreadsheets that are linked to CAD, and like you can tell us what your extrusion system needs to do, and we can crank you out an extrusion system that will do that.
Okay.
And so that's what makes us great, is like more of the understanding fundamentally what we do and conducting more and more like fundamental research into how all of that occurs is very important to us. But in terms of a commercial maker shift, it's undeniable that a large portion of our revenue comes from selling to printer manufacturers. But the majority of the printer manufacturers that we sell to are maker-oriented printer manufacturers. I think it's more that it's less that we are not catering to the maker community. It's more that the maker community wants to buy like, working functional good printers by default. And if your printer already comes with an E3D hot end on it, then there's not much impetus to change it out for something else. So we're focused on making systems that are great by default, but will also enable a good degree of post-sale interaction, because at the moment it's kind of difficult, and a good competent maker has no great beef with changing out a nozzle, but it's still kind of inconvenient.
Right.
Even for you or I, changing out a nozzle is inconvenient. And so, yeah, we've got to focus on kind of usability and cost. Everyone wants things cheaper, but making things more and more usable is kind of neat, because we can allow people to do more with their printers more easily. And so that's kind of where our focus is going. But those systems are still targeted at makers just through the vector of selling to maker-oriented printer manufacturers.
Yeah. And I think that was a good move on you guys' part. Like, you saw where the market was going, and it's very different than it was when you and I got into it 5-6 years ago. There's far less people building machines out of random stuff that they bought at Home Depot, and far more people going out and buying Ender 3s. So
yeah, and I mean,
it's sad.
There are plenty of things. Yeah, but say what you will. I mean, there are plenty of things wrong with Creality or what have you. But the Ender 3 prints pretty damn well.
It does. It hurts to say.
It's got to be said.
It hurts.
That thing, in terms of a cost to performance ratio, damn, that thing is good. It's scary good. And so these are realities. And we have to deal with our principles and where we came from and who we are and what we do, but we also have to cope with realities. And the reality is that we don't want to cater to the race to the bottom, but there's a trend.
Yeah.
And we have to ensure that our business still functions in those macroeconomic trends that the market is undergoing. And the big trend that we're seeing is more usable and lower cost. And we have to make systems that will fit in with that. Otherwise, we will be crushed and we will die.
And that's the sad reality. But it's, doing that is what is enabling you guys to do fun stuff like the tool changer.
Yeah, but I mean, but also this is what we're going to do is really cool. We're going to combine all these multiple parts of a hot end into one single unit that we automatically robotically manufacture in-house in a vertically integrated system from raw materials. It's some real Elon Musk Tesla grade shit going down. We're talking one roof, ceramic coming in boxes, and bar stock coming in, and bits of tube and ceramic insulation and heating wire, and automated assembly occurring, and amazing low cost, easy to use little hot end things coming out the other side.
I love it.
And that means that we're generating the most value because we're doing the most in-house.
Right.
So we're generating the majority of the value, which is good for us commercially as a business. But from a technical perspective, it also affords us the greatest degree of control possible. We can tweak everything in the system. We don't have to go and beg our heater manufacturer to can you please go and do that or use this other wire? And they'll be like, yeah, I don't really want to because I've got a big order coming. No, we want to play with a new thing. We can play with a new thing.
Yeah.
So the degree of technical control is really cool, and I think it's going to allow us to do things that are really quite impressive in the consumer hot end world. Hot ends that heat up like that and have absurdly good temperature control and allow us to get huge amounts of thermal flux into the polymer in short spaces of time and space.
Excellent.
It's not boring. It's not just paying the bills boring stuff. There's some good hard science to dig our teeth into there, and I'm finding it very fun.
Oh, good. That's what matters. Well,
yeah.
Do you have other things you want to talk about? We you know what?
I can dance all day. I can dance all day.
What's it gonna take to get to the next level for printing? We've got really good mechanical platforms. Everyone can build a damn solid gantry that can print excellent benchies all day long.
Yeah, I mean, there's no fundamental advances to be made in motion systems. As far as I see it, motion systems, we've been doing motion systems, good machine motion systems since the 1700s when like we started making good metal lathes,
Right.
and then subsequently milling machines. And then since the 60s, we got CNC and servos, and everything there is like we just need to read the textbook properly, and you can make a good motion system.
Yeah.
Unfortunately, people haven't been reading the textbook properly for the last 3 years, and there have been some horrors, but that's kind of being worked out of the system now, and things are going okay. As far as I see it, there are three fundamental things that permit like the core advances that make 3D printing what it is. One is materials. We have to have materials that print exceptionally well and have exceptional end-use properties. The second is software, and software is probably one of the largest single enablers. It's worth bearing in mind that a piece of software controls absolutely every aspect of how your part comes out, how strong it is.
Yes.
In a way, the design that you put in doesn't really matter. How the software interprets your design is what really counts. And so I think there's going to be some huge advances there, but that's going to require a revolution rather than incremental approaches. I think that slicing is, like Cura, for example, or remember the Ski Forge days?
Oh yeah.
Right? And Rep Snapper and stuff. Like we started out like, well, we've built this like facsimile of a 3D printer and we need something to drive it. So let's create something that can slice a cube. And we went from slicing a cube and then we like put in bridging and support material and infill patterns and stuff. And Cura was based on SkeenForge, as I understand it, which was like the original, and they converted it to run on PyPy and then and then it became Cura. But we still have, we take the 3D model, we slice it into layers, and then we do 2D operations on those layers, and off we go. There's a lot more to be done there, I feel.
Like whatever happened to non-planar slicing? Like that. That's such a cool idea and so fundamental to how our layers are formed and how our strengths are done.
And I think it's hard because DFM for that is hard. As with many things, and I think that 3D printing abstracts away from CAM very well, in that you never have to it trivializes the CAM process, which is kind of its biggest advantage because it's backwards. So,
but at the same time, it makes people think that CAM is just clicking print, and it's like, oh no, you actually have to tell the machine what to do.
People going from 3D printing, like from additive to subtractive, have this rude surprise when they can't just put the model into the slicer and then the automatic tool changer and the 5 axes just get to work. A rude awakening. But I think that we could do with a little bit more of like CAM in 3D printing. Like I want, let's get rid of STLs and steps, and like I want this boss to be printed in this way, and I want all this kind of control.
There was for a while there were all these efforts going on to do like 3D printing specific file formats like AMF, and there were a couple others.
Step. just stop. Just give a step.
Just give me a file format that I can click on a feature and say, I need this hole to have 8 perimeters, and everything else doesn't matter. This hole needs 8 perimeters. That's all I want.
I know, dude. Or like between these holes, I need to like reinforce. It's like one of the cool things that I think Mark Forge does is like between these holes, I need this amount of load capacity in tension, and then I'll string enough fiber around those holes.
Like, oh man, that was one of the things I wanted to talk about. Like continuous fiber. Like, get rid of all the chops. It seems like every chop and filled filament I've used, it's just weaker than its original base material because the chop screws with the polymer bonds.
I think there's some material science that needs to be done there to sort that out. Like if we look at injection molded fiber filled parts, they have higher tensile strength than their unfilled brethren, as well as higher moduluses and things like that.
But those are.
Watch this space. We've got some cool stuff coming out, but essentially the interactions between the fibers and layer adhesion and some other things result in poor properties. There are ways of solving that by changing the way the material flows.
I'm trying not to dive too deep into material science because you guys, Thomas, how do you say Thomas's last name?
Sandlader.
Yeah, what Sanjay just said, and Rich, they did a really awesome podcast a week ago, 2 weeks ago, on the Melt Zone. And there was an audio mishap, but seriously, sit down and listen to it because if you're a materials nerd, that was a great session. But like, what do you think it'll take to do continuous fiber on a desktop? I mean, not buying a Markforged, but like you and me.
Yeah, I'm not sure because as far as I'm aware, if you're pushing continuous fiber thermoplastic continuous fiber out of a heated nozzle, I think that you're covered by the Markforged patent.
Oh.
I am not a patent lawyer, so I don't know that in depth, but I believe that to be the case, and so that's why we haven't worked on any fiber systems.
Okay. So I saw a university project on it 2 years ago. But those patents may have come out since then. But they were fluidizing carbon fiber and running it down with a UV reactive resin, and that was really neat.
That's cool. So they're like what? They vibrate it, so it kind of.
It was it was seriously, they were it was like a paste extruder, but they had a continuous strand of carbon fiber inside the paste extruder, and they got it started and then coiled the carbon fiber into the syringe and then filled the syringe with this resin. And
that's cool.
Yeah, and they were just plunging it, and as the resin came out, it would feed out the carbon fiber, and then they were able to build it up. And I saw it because it was when I was working for Lulzbot, and they were using a TAS 6 as their motion platform, which I thought was super neat. But yeah, that was a really simple design for a labby type experiment, but it seemed like a relatively easy concept to bring into a product for engineering purposes. But it takes a while to go from the lab.
I know of people that the things that I can't disclose, but I know of other people attempting continuous fiber systems. But it's something we're kind of staying out of. I would love to, because there's obviously these amazing performance gains. We'll see how that kind of plays out. But it's not something that we're getting involved with. Maybe we should go reread the patents, and we'll have some. But as far as I see it, if you have a nozzle, you have thermoplastic, and you have continuous fiber, and it's coming out of the nozzle, I think that you're covered.
Okay, well, that's a good reason to not do it. People are taking patent law pretty seriously right now, so.
Yeah.
Well, hey, that's the end of my list. We're definitely past the hour mark now. I don't want to hold you for any more time. Do you have anything else that you want to talk about that you want to, while you have a platform?
I think Rory's designing an A and B axis for the tool changer.
What?
Yeah. That's a cool. That's very early stage. So we have this thing called like Wonderful Wednesdays, where the engineers get to kind of work on their own thing. And that's Rory's Wonderful Wednesday project at the moment.
Well, tell Rory if he needs help. There's a guy that's a few hours off from him that is in.
Yeah. Um, yeah, I haven't seen it. I don't know if it's like Trunnion or what have you.
That would be the easiest way. I was trying to get when I worked for Cat, I was trying to get them to fund me for 5-axis printing, and not necessarily coordinated motion, but just simply reorientation of the build platform.
Yeah. So 3+2 is fine.
Yeah, that would be amazing for getting your strength vectors in the right direction, but it brings up a
Yeah.
huge software challenge, and it would be
Enormous.
a really fun one to
Enormous.
work with. So
Yeah. Um, but yeah, I think that if we have this like merging of CAD and CAM for FDM, then we can start to do some cool things because we can, break up parts into sets of features and decide that this will be done in this orientation and so on. So I have faith. I would like to see ultimately something that's kind of like HSM that's been integrated into Fusion, but instead of removing material, you're adding it. That doesn't seem like an enormous step. And I'm always shocked that HSM don't have a slicer, right?
well, they have NetFab that's kind of like being integrated. I wouldn't be shocked if it was like in the pipeline. Based
Yeah,
on some
yeah,
conversations I had with them at IMTS, I would not be shocked if that wasn't coming down the road.
yeah.
But
I would not be shocked if Autodesk just came out with a slicer, right? But I I just, if I was them, I would have done it already or acquired one. The guy who made Mesh Mixer, because he's sold to
mm-hmm.
Autodesk, but he's now no longer with Mesh Mixer. He's doing a really cool looking new slicer. You seen that thing?
Uh-uh.
Um,
Do you know what it's called?
it's got a weird name.
Of course it does.
Um,
It's 3D printing. Why should it have a straightforward name like thing that makes parts? Slicing software 3. Um, Yet the current iteration of NetFab that Autodesk has out, it brought in the Spark Studio stuff that they were doing for a little while. So you can slice with normal FDM printers. It's just not super straightforward to set up printer profiles for the ones that they don't support. Which like they support like Ultimaker and Type A and a couple others, but nothing.
so who's this? Which package is this?
The Autodesk with their newer NetFab
Oh, I
that they're
see.
doing.
Yeah. So you know that NetFab had a slicer for Ultimaker 2s before Cura, I think, existed.
It's probably
So
built on this. This is probably built on that slice engine.
yeah, so Ultimaker used to sell NetFab the slicer. Um,
Huh.
yeah, back in the day, that was a thing.
That was a Wednesday for those that don't know.
Yeah.
Well,
I'm trying to find the name of the slicer for you.
if you find it,
But
shoot it to me over email or whatever. I think we should probably wrap up.
I think that's probably sensible at this point.
Because at this point I am very late for work.
Oh, dude. Yeah, sorry.
It's fine. It's fine. I'll make it up. But with that, this was Joe for Makers on Tap with
Sanjay Mortimer from E3d Online.
And if you have any questions for me or Sanjay that came up out of this interview, hit us up on our social medias. The subreddit is r/MakersOnTap. We're on Instagram, also as Makers on Tap, and same for Facebook. And if you thought this podcast was awesome and you want to let your friends know about it, share us all over the internet. We like it when people let us know that they like us by doing things like commenting and
Oh yeah,
sharing.
we'll have to put you up on Twitter, man.
Yeah,
Well, make sure we post.
we need to get a Twitter. Maybe I'll do that today. All right.
Yeah, do it.
So with that, I'm out. Thank you guys, and keep making stuff.
Yeah. Thank you very much, Joe.
And we're back. So you guys made it through the interview, hopefully. If you didn't, maybe you skipped to this timestamp. I had an absolute blast talking to Sanjay, and we've actually since then talked about making this a recurring thing every couple of months where we just like ramble on some rabbit holes and see where they go and have some fun with it. But what did you guys think?
Absolutely. Just the conversation I immediately like posted in our kind of like group discussion, like I was really sad that I missed out on this opportunity to talk with Sanjay because like he just seems like such a cool guy to talk to, especially when he's drinking, because of just the train of thought that man has of like connecting things is incredible. And just listening to some of the theory stuff and him getting so excited about that was just like really kind of, wow, this guy is really passionate about this. And you can actually tell it's not just this PR kind of thing of like, oh no, I need to be excited about my job. You can genuinely tell like he is excited to like go home and also continue to engineer and continue to make stuff in his own personal life. And he just continues to like carry that on throughout his day. So it was really fun. It was a really fun interview to just listen through and kind of listen to all of the different rabbit holes, but also cool things that are coming in the future.
Well, and Sanjay is kind of like us, where he's a maker in his professional life, and that just never ends for him. Like it's just a continual stream. And the main difference between him in this interview and him with a couple beers in him is the stream of consciousness is harder to butt into, and it gets a little more interesting, just because he gets a little more like, but what if we try this?
Well, and that's the funny part was you could even tell like during the interview he was already having like trains of thoughts of like, oh, that would be interesting, or that would be kind of cool to try out. And it was just like that was kind of cool to just see those gears kind of churning on a professional level and all that kind of stuff. It was definitely a fun interview to listen to.
Yeah, I was also sad I kind of missed it. I'm looking forward to the next ones.
Yeah. About 30 minutes before the interview started, Aaron sent me a text and was like, hey, I'm not going to make it. Try not to let this get too technical. It's just like, no. Yeah. I'm going to let it go where it goes.
It wasn't too bad.
No.
You both were actually pretty good with, at least he was, explaining the overall details of what the high level of what he was about to go into. Like, for instance, the Stadia. The Stadia of the film coming out, and I personally did not know that, so it was nice that he did the technical side, but also broke it down, so then you can at least follow still. So that was nice.
Yes, that's what's so much fun about to talk to any of those guys. If you go talk to them at trade shows and stuff, that's how all of them are in person. Is just super fun and super willing to break things down if you don't quite understand. Very down to earth and really great guys. So.
No, absolutely. It was really cool. Also, especially getting follow-up from one of the earlier news episodes we had done a little bit ago on the new tool changer. We got a lot more detail into that, and even some possible things coming out for that we didn't even have details on back then. So it's kind of cool, especially like me being the very much noob on that, not knowing a whole bunch, hearing it directly from Sanjay, and being like, hey, this is actually what we're looking at. This is what we're trying to shoot for. And just getting clarification on that. This is very much a tool for you to be able to put on things, not necessarily a kit out of the box. And them reinforcing that of like, this is what we're shooting for and all the things that we have possibilities for, but really you have to implement that on your own machine. Yeah. So it's cool. Like we kind of like did this news story a little bit ago, and we were kind of like, this is cool. We really want to like see more stuff. And now a little bit more episodes down the line, we're actually seeing like, hey, this is what we actually are doing. So it's kind of cool continuation from one episode to another. And I don't know, I kind of like that we're building this little kind of cool thing between the episodes now. So yeah.
I'm really looking forward to the end of November when one of those shows up in Illinois. at my house.
Is that like, is that part of the, because I know you said, I don't even know what the beta 30 is. He apparently made fun of you for that.
Oh no.
But
yeah. Joe gets special access to buy into this beta program and gets one of these motion platforms like the sucker he is.
Yeah, I'm a total sucker. I'm a total fanboy. It's fine. No, beta 30 is, like you said, they're building 30 beta units as a release candidate, just to make sure that when they release them to the real world, that they work, and that the couple that they've built in-house so far work like they expect when they ship them out to a whole bunch of people. So I'll be one of the first 30 to get one, and then after that they're going to do a release of 100, and then they'll go into full production if beta 100 works out. So
wow, okay, no, that sounds awesome. I really hope that maybe after full release we can definitely get him back on to just hear about the process of how they went through the whole thing, and just like all the cool stuff that went into it, because it definitely, as much of it sounds like a tool that they are using for commercial use in some aspects, they are definitely still trying to make it for makers as well.
Yeah.
And he kind of made that clear. He's like, it may not be for you, but there is people out there who this is exactly what they need, and we are trying to make it as best for them as possible.
And we might have him back on for that, but I feel like our podcast covers like a whole different world with these guys, like the Tom's 3D and the 3D printing nerds and all those guys. They do such a good job of covering the commercial things and and all of that. But we've been able to keep all of these so freeform and really fun and very conversational. I'm hoping we can keep that instead of just becoming industry news like everyone else.
Right. I really enjoyed all the personal questions you asked him. Like, that's the kind of stuff that I want to get into. Like, why are you the way you are? Talking to all these industry maker professionals, like anybody else could talk about products and design and stuff, but what makes you tick, and what gets you excited when you get home from work? That's stuff that I like to learn.
Because you got to remember, like the three guys that started E3d, Sanjay, Josh, and it'll come to me. Sanjay and Josh are the two that I talk to very regularly. They came out of university and then they started building hot-ends in their basement. Like the original E3d hot-ends were just a project that they made in their college machine shop and released on the RepRap forums. They're us. They're just incredibly brilliant, successful us. So
ouch.
Yeah, right. I know.
My feels.
You feel identified. Yeah, a lot of the interviews that I'm trying to line up are people that have been passionate about a project and made it, and been able to create something great, and then share that with the world and kind of be inspirational, But
no, absolutely.
Okay, this is officially the longest episode that we've ever released, and it has the least amount of us in it. So if we want to recap more, we can definitely do that next week. There's a ton of news that we wanted to get to, but I kind of feel like we should leave it at this point and get it next week. So with that, this is Joe.
And Aaron.
And Christian.
Keep making stuff, guys.